Hey there everyone. Today's lesson is on 7.2.2 Ellipses and Eccentricity. Bonus points for alliteration today in the title. The eccentricity of an ellipse is basically the ratio of C to A. And we already talked about what C measures and what A measures. I like to think of the eccentricity as a measure of how round or how oblong the ellipse is going to be. So here's a great visual to show you how, as you change C as it relates to A, how it makes the ellipse rounder and rounder and rounder. And so over here on the left side, you'll see that the distance to the foci, right, C, is really close to the distance to the vertex A. So as you move those vertices out further and further away from the center, as you move the foci out further and further away from the center, you can see that it really starts to pull the ellipse into this really narrow egg shape. And that right there shows you the eccentricity. It's 0.94. It's almost 1, which means C is almost the same length as A. But as we decrease C, as we make C smaller and smaller and smaller, the ratio gets lower, and we start to round out our ellipse. And here, as you get closer and closer to the center, as the foci is closer and closer to the center, you can see it's almost a perfect circle until the actual foci are on the center. And we talked about this in class the other day, that if the foci are exactly on the center of the ellipse, then that creates equivalent distance for A and B, and you get an actual circle. And so today we're going to be discovering how to express the eccentricity. It will always be a value between 0 and 1. If it's anything more than that or less than that, then you've broken the ellipse. Okay, good for you. You can't have any values greater than 1 or less than 0 when you're solving for the eccentricity if it's a true ellipse. Alright, so our formula for the eccentricity is all you do is you solve for C, which is the distance from the center to the focus, and you find the distance A, the distance from the center to the vertex, and you create a ratio with them. And usually we express it as a decimal. So we're going to start with example 3. It says to determine the eccentricity of the ellipse given by x minus 6 squared over 100 plus y plus 1 squared over 9 is equal to 1. And so we're going to want to start the same way that we were, as if we were figuring out how to graph this. Even though we don't need to graph it, it's helpful to know where the center is. The center is going to be located at 6, negative 1. We need to figure out what a squared and b squared are. A squared is the larger denominator, which is 100. B squared is the smaller denominator, which is 9. So that means A is equal to 10, and B is equal to 3. And because A is underneath my x minus h squared component, that means it's going to be a horizontal ellipse. That's going to be useful as well. Because if it's a horizontal ellipse, that means my major axis runs left and right, and that means my foci also run left to right of the center. Once you know A and B, you can solve for C. C is always going to be c squared plus b squared equals a squared. Remember, it's not the traditional setup for Pythagorean. We're used to calling C the hypotenuse, but in an ellipse, A, the distance from the center to the vertex, is always the largest side, and so that's always going to be your hypotenuse. So we can solve for C, the distance from the center to the foci, by plugging in A and B here. So c squared equals 3 squared. C squared plus 3 squared equals 10 squared. And so it kind of seems silly that we even solve for A and B since we're going to square them again. This becomes c squared plus 9 equals 100. And so c squared is equal to 91. So c is the square root of 91. Once you solve for c, it's really easy to find the eccentricity using your formula. The eccentricity E is equal to c over A. So we just plug in c and A. C was the square root of 91. A was 10. And so we almost always express this as a decimal, so I'm taking out my calculator now. I'm going to type in square root of 91 divided by 10. 0.95. You can just round to 2 decimal places, and that is a pretty narrow ellipse. That means that the distance from the center to the focus is almost the same as the distance from the center to the vertex. And that makes sense because look how much bigger A is than B. It's going to be a very narrow ellipse for this one. So it's got an eccentricity of 0.95. Alright, that's all you have to do. Try A and B on your own. Okay, the solutions would be the eccentricity for A is 0.79. Your C, distance from the center to the focus, should have been square root of 30. And for B, your eccentricity is 0.32. Your distance from the center to the focus was really small, it was only square root of 2. And this would be much, much closer to being circular than this one, right? Remember, the closer the eccentricity is to 0, the more circular the ellipse is. Okay, the other thing we're going to do in this lesson is we're going to be talking about how to determine different types of conics by putting equations into their standard form. We've already identified parabolas and we've already identified ellipses, but we haven't looked at the standard form of a circle yet. It's very similar to that of an ellipse. You still have your x minus h squared and your y minus k squared, but instead of dividing by a squared and b squared, since a and b are the same in a circle, they multiply it over, and they don't call them a and b anymore, they call them r, because that's technically the radius of the circle now. So if you find yourself putting it in standard form and the equation simplifies to something like this, it's technically a circle now, no longer an ellipse. So we're going to practice putting these into standard form. Right away with A, I can tell that A is going to be a parabola as I'm setting this up. And I can tell that because there's no y squared. If you just have one variable squared, it's pretty obvious that it's only going to be a parabola. So I'm going to go ahead and set up, this is kind of a review from our previous section, my x squared minus 6x. I'm going to add the 2y and subtract the 5 to the other side. So we've got x squared minus 6x is equal to 2y minus 5. And I need to complete the square here, so I know that if I have a negative 6x, then I'm going to, when I find my perfect square and factor it, it's going to be x minus 3 squared. And so I can square the 3 and see I need to have a 9 here. So I need to add 9 in order to be able to factor it to get this squared binomial, so I need to add 9 to the other side. And so we get x minus 3 squared is equal to 2y plus 4. And lastly, I just need to factor out the 2 to put it in standard form. This is going to be 2 times y plus 2. And now we can see h and k, and we could, if we needed to, we could identify the vertex and then the focus of the parabola. But all they wanted us to do is put it in standard form, so we're done. And it just has to identify it. So you just want to write that this is a parabola somewhere as part of your answer. Okay, that was easy and pretty much a review of what we've already done. Let's try another one where we actually have an x squared and y squared. So this is similar to the one that we did on Monday. We're going to reposition these. This is x squared minus 12x plus y squared plus 10y. And then I'm going to subtract the 12 over so that it's set equal to negative 12. This one's nice and easy because both x and y have 1 for their coefficient, so I don't have to worry about any parentheses and incorrectly completing the square. Half of negative 12 is negative 6, so this is going to factor to be x minus 6 squared, but I need to add 36 in order to do that. So I'm going to add 36 to the other side. And then to complete the square for y, half of 10 is 5, so this is going to be y plus 5 squared. I need to complete the square for this one by adding 25. So negative 12 plus 36 plus 25, that's going to be 49. Now, if you can't tell, this is actually going to be a circle, because if I divide both sides by 49, this is going to be x minus h squared over 49 and y minus k squared over 49. That means a and b are going to be the exact same. There's nothing to reduce with those fractions. So this is actually in its standard form already. This is in the standard form of the circle that we see up above. So it would be a circle. The center of the circle would be at 6, negative 5, and the radius of the circle would be 7. And you don't have to write that r is equal to 9, but I'm doing it just so that you remember how to solve for the radius given the center. Just make sure you take the square root of that part. And finally, we have one with an x squared, a y squared, and an x but no y. So let's see what happens in this scenario. We're still going to position together all of our variables that are alike. So x squared minus 6x plus 4y squared. And I'm still going to add the 7 over to the other side. And so I add the 7 over. And now we need to complete the square. The one that's easy to complete the square for is x squared minus 6x. because there's no coefficient out front, so we add the 9 and add the 9 to this side as well. And so we factor this is going to be x minus 3 squared. But now I have this 4 times y squared. I'm going to need to rewrite this so that it's a binomial. And we've done that before with parabolas where we just stick a 0 in there. And now that's technically a binomial. And it looks a lot closer to the form that I'm used to seeing. 7 plus 9 is 16. But I have a coefficient out here, so I'm not probably going to have a circle. But if I divide both sides by 16, I'll see how it turns into the general form for an ellipse. And sure enough, when we divide by 16, the right side becomes 1. 4 over 16 reduces to 1 over 4. And you can either leave the 0 or get rid of it. It doesn't really matter. It's going to be y squared over 4 plus x minus 3 squared over 16. Don't let the fact that k, right, k is 0, screw you up from recognizing that this is still an ellipse. Okay, and that's how you identify, just by looking at the equations, what type of conic you have. Right. Here are 3 more to try completing on your own. Okay, here are each of the examples written out step by step how to get to their general form. First one was again a parabola. You completed the square by adding 9 to both sides, and then make sure you factor the 3 out of the binomial on the right side. For the second one, you get a unique kind of circle. Notice that you do have coefficients on both your x and your y, and they're the exact same coefficient. So you can actually divide both of them by 4 and then get it into the general form for a circle. If you divided the 64 over first, thinking that it was an ellipse, hopefully you realized once you simplified that they both a and b were the same. You should have gotten that both a and b were 16, and then you could just multiply the 16 over to the other side and get your radius is 4. And for the final one, it was an ellipse. When you completed the square for that one, you only had to complete the square for the y term because x was already able to be written as a binomial. Yeah, you complete the square for the y, and then you find out that you can reduce both of the fractions, and you should have gotten a squared is 16, b squared is 12, and it forms an ellipse. Okay, that's it for today's lesson. The assignment that we're going to be working on tomorrow is right here, if you'd like to get a head start on it. If not, I'll see you guys tomorrow.